The Earth, our home and cradle. The only place where we can live. A fragile yet marvelous planet that has fostered the development of life. While Earth has been our cradle, it is not certain that it will remain our home forever. Exploration is in human nature. Thousands of years ago, we sailed the seas in search of new lands. And today, we cannot help but think of a future among the stars. But is it really possible for humans to leave their home? Can we truly pursue the dream of becoming a multiplanetary civilization? Space colonization, a theme dear to science fiction, is now on the cusp of becoming reality. Humanity is at a turning point, equipped for the first time with the technical knowledge to realize this dream. The future of humankind lies among the stars, and the beginning of this incredible journey could start today. But there's a problem, what scientists call the Great Filter. The concept of the Great Filter is one of the most fascinating and unsettling in the discussion about extraterrestrial life and humanity's future. It attempts to address the Fermi paradox. If the universe is so vast and old, why haven't we found traces of alien civilizations? This concept suggests the existence of an extremely difficult or impossible barrier in the evolutionary path of an intelligent civilization, preventing their expansion into the cosmos. The Great Filter might be in one of the evolutionary stages. From the formation of simple organic molecules, to the emergence of life, to the development of a technologically advanced civilization. If the filter is behind us, it means we're exceptionally lucky. But if it's ahead, the future may hold almost insurmountable challenges. For humanity, the Great Filter could take many forms. Catastrophic climate changes, nuclear war, uncontrolled pandemics, or the unsustainability of our consumption practices. It could even be something unimaginable. A hurdle that only becomes apparent when we're about to face it. Our own technology, which has marked our ascent, could be the Great Filter. We might be destined to self-destruct with the very inventions that have led to unprecedented progress. Runaway artificial intelligence, biotechnology gone awry, or destructively used nuclear energy are all potential examples. The Fermi paradox poses a disturbing question, and the Great Filter might be the answer. Perhaps other civilizations failed to overcome it, thus explaining the cosmic silence surrounding us. But if we manage to navigate this delicate phase of our existence, then we might truly begin that wonderful journey that could take us among the stars. This invisible challenge, woven into the fabric of our progress, represents the fine line between our survival and our ruin. Imagine a universe where humanity is one of the few civilizations to pass the Great Filter, earning the prestigious pass to reach the stars. Or conversely, envision us standing before a dark abyss, where an apocalyptic event awaits to erase our existence. History brings us back to a pivotal moment, the end of World War II. With the advent of nuclear weapons, a window of danger opens. A period of uncertainty and potential self-destruction, where nuclear wars, biological conflicts, or anthropogenic climate disasters could mark the end of our era. At the heart of this scenario lies the possibility that the Great Filter is still ahead of us, an invisible wall towards which we are unknowingly hurtling. A time where every choice, every action, might be the key to our salvation or the signature of our doom. But there's also hope. If we manage to overcome this critical phase, the future beckons us. Researchers at NASA have crafted a model, a stellar path, that foresees our expansion into the solar system and beyond. This model is the compass guiding our deep space missions. The goal? To transform humanity into a multi-planetary species, colonizing new worlds to ensure our long-term survival against calamities, both natural and self-inflicted. A bold dream, a challenge against time and space that might finally free us from the chains of our earthly cradle. This is the story we tell today, a tale of courage and survival. A saga where every decision shapes our destiny. An epic journey into the unknown, where humanity might finally claim its place among the stars. The model developed by NASA researchers is built on empirical data collected from past and present space missions. This data provides invaluable insights into the current and future capabilities of space technologies, from launched vehicles to support infrastructures. A novel aspect of the model is the use of computing power as a key factor. Computing power is measured in transistors per microprocessor, an indicator of a computer's processing capacity. This parameter is crucial because the complexity and success of space missions are closely tied to the available computing capabilities for simulation, control, and management of space systems. Using this data, the model attempts to forecast the various stages at which human crewed space missions to different destinations could occur. This includes journeys within our solar system, like to Mars and Jupiter's moons, and potentially missions to nearby star systems, such as Proxima Centauri. The model is based on the assumption that current trends in space technology and computing power will continue into the future. It predicts that, as computing power increases, it will become possible to design and execute increasingly complex and ambitious missions. The projections of the model are not just predictions of when we might travel to specific destinations, but also a roadmap for research and technological development. It highlights the areas where investment and innovation are necessary to make large-scale space exploration feasible. The vision of space exploration, as outlined by the model, unfolds along an ambitious and breathtaking timeline. Here are the milestones of this epic space odyssey, outlining key years and anticipated achievements. The decade of the 20s and 30s marks a significant turning point in space exploration. A period characterized by technological advancements and strategic collaborations that lay the groundwork for the future of human space exploration. During these years, we witness a significant evolution in launch technology. New rockets are more powerful, efficient, and reusable, significantly reducing costs and increasing the frequency of launches. This includes the development of heavy-lift launch systems, essential for transporting crews and equipment needed for long-duration missions like those to Mars. Life support systems for spacecraft and space stations become more advanced. These improvements include more efficient water and air recycling systems, as well as techniques for food production in space, which are vital for long-duration missions away from Earth. The decade also sees the development of new materials that can better withstand the harsh conditions of space, such as extreme radiation and variable temperatures. These materials help ensure the safety and longevity of spacecraft and their components. A key aspect of this period is the increase in international collaboration and private sector involvement in space exploration. Space agencies from different countries and private companies collaborate, bringing diverse expertise and resources. This combined approach accelerates the development of new technologies and the implementation of ambitious missions. Research and development of new forms of space propulsion gain momentum in this decade. Ion engines, offering greater efficiency compared to traditional rocket engines, are among the most promising technologies. These engines are ideal for long-duration missions and could revolutionize how we travel in space. All of this culminates in the growing focus on missions to Mars. With the necessary infrastructure and technologies rapidly developing, the 2020 to 2030 years lay the foundation for the human dream of setting foot on the red planet. The period of the 30s and 40s marks a critical era in space exploration, characterized particularly by the achievement of a historic milestone: human landing on Mars. The realization of a human landing on Mars relies on significant improvements in the efficiency of space travel. This includes optimizing flight paths to reduce travel time and fuel consumption, as well as improving propulsion systems for greater speed and reliability over long space voyages. To safely land on Mars, more sophisticated and precise landing systems are developed. These systems are designed to handle the complex dynamics of landing on a planet with a thinner atmosphere than Earth and potentially unpredictable terrain. Once on Mars, creating sustainable habitats becomes a priority. This involves using advanced technologies for in-situ resource utilization, ISRU. For example, extracting water from Martian soil and producing oxygen through chemical processes like electrolysis or the Sabatier reaction becomes essential for long-term survival and reducing dependence on Earth. Technologies enabling the utilization of Martian resources play a key role not only in providing vital resources like water and oxygen, but also in producing building materials, rocket fuel, and other essential goods. This helps establish a sustainable and self-sufficient human presence on Mars. In parallel with crewed mission advancements, robotic missions continue to explore Mars and other celestial bodies. These missions are crucial for laying the groundwork for future human explorations, mapping the terrain, searching for resources, and conducting preliminary scientific research. The data gathered from robotic missions and the first human expeditions to Mars provide valuable insights for future explorations. This period lays the foundation for more ambitious missions, which could include exploring other planets, moons, and asteroids. The period from 2040 to 2060, known as the Dance of the Asteroids, represents an era of extraordinary innovation and discovery in space exploration. During these years, the asteroid belt, previously considered an inaccessible and mysterious region of our solar system, becomes a new frontier for humanity. The first step towards asteroid exploration is the refinement of space navigation and propulsion technologies. Navigation systems become more accurate, enabling spacecraft to maneuver through the complex trajectory of the asteroid belt. Space propulsion makes significant strides, with the development of more efficient and faster engines, reducing travel times and extending the reach of missions. The asteroid belt attracts attention not only for its scientific importance, but also for its economic potential. Asteroids are rich in minerals and precious metals like gold, platinum, and rare elements, making them attractive targets for space mining industries. Moreover, studying asteroids offers unique insights into the formation of the solar system and planetary history. Missions to explore and exploit asteroids rely on advanced robotic technologies. These robots, remotely controlled from Earth or operating semi-autonomously, are equipped with instruments to analyze the composition of asteroids, dig, extract, and process materials. These robotic systems are designed to operate in extreme conditions, including low gravity and exposure to radiation. The exploration of asteroids paves the way for the exploitation of their resources. This can include extracting water for life support and rocket fuel production, and precious metals. This activity not only has the potential to be economically beneficial, but can also provide essential resources for further space exploration and colonization. The techniques and technologies developed for asteroid exploration have a significant impact on future space missions. The ability to utilize in-situ resources in asteroids could serve as a model for other missions, including those on Mars and beyond. In the period from 2060 to 2080, missions to the moons of Jupiter and Saturn represent one of the boldest human adventures in space, challenging the limits of technology and our understanding of the universe. The extreme conditions of the icy moons of Jupiter and Saturn necessitate the innovation of new landing systems. These systems must be capable of maneuvering through thin or non-existent atmospheres and landing safely on slippery and irregular surfaces, dominated by ice and rock. The engineering of the landing system involves careful consideration of the low gravity and complex geology of these moons. One of the most exciting scientific objectives of these missions is the exploration of the subterranean oceans believed to exist beneath the ice crusts of some moons. To study these oceans, specialized instruments capable of drilling or melting through the ice and sending robotic probes or underwater vehicles to collect data and samples are developed. The great distances to Jupiter and Saturn require more efficient and effective forms of propulsion than traditional rocket engines. Nuclear engines, offering greater efficiency and shorter travel times, emerge as a promising solution. At the same time, advanced electric propulsion systems, such as next-generation ion engines that provide constant and sustained thrust, are developed, ideal for long-duration deep space missions. Dealing with the extreme environmental conditions, such as intense radiation near Jupiter and cryogenic temperatures, requires the development of protective technologies to ensure the safety of instruments and, in any future crewed missions, human life. This includes advanced radiation shielding and thermal insulation systems. These missions are not only technically revolutionary, but also have the potential to transform our understanding of life in the universe. The possibility of finding life, even microbial, in the vast subterranean oceans of these moons could answer the centuries-old question: are we alone in the universe? The period from 2080 to 2100 marks a new era in space exploration, where the goal becomes extending human presence beyond the bounds of the solar system. The key to reaching the farthest parts of the solar system and beyond lies in advanced propulsion technologies. Nuclear fusion propulsion emerges as a promising technology in this area. Unlike traditional rocket engines that burn fuel to produce thrust, a nuclear fusion engine combines light atomic nuclei to release vast amounts of energy, providing much more powerful and sustained thrust. This type of propulsion can drastically reduce travel times and open up new possibilities for interstellar missions. For missions of such extended duration, highly advanced and autonomous life support systems are necessary. These systems include technologies for water recycling and purification, space-based food production through hydroponic or aeroponic agriculture, and advanced waste management systems. Additionally, radiation protection and the physical and mental health management of astronauts become crucial components for the success of these missions. This period may see missions directed towards targets such as the Kuiper Belt, a densely populated region of icy bodies, and the Oort cloud, a spherical shell of comets believed to surround our solar system. The exploration of these regions could provide fundamental information about the formation and evolution of the solar system, as well as the composition of comets and other icy bodies. As we explore the farthest reaches of our solar system, the technology and knowledge gained serve as a launching pad for future interstellar missions. The ability to travel faster and sustain human life for extended periods in deep space is essential for missions to nearby star systems, like Proxima Centauri. This period represents not just technological advancement, but also a significant step in the evolution of humanity as a species. With human presence extending beyond Earth, humanity moves ever closer to becoming a true multiplanetary civilization, a fundamental step in our aspiration to become an interstellar species. The journey towards Proxima Centauri, a voyage that takes us beyond our solar system, represents one of the most daring and revolutionary challenges in space exploration. This endeavor requires a true technological revolution. One potentially groundbreaking technology for interstellar missions is the photonic propulsion engine. This type of engine utilizes the pressure exerted by photons, particles of light, to create thrust. Although the idea of using light for propulsion may seem like science fiction, advancements in physics and engineering could make this technology a reality. A photonic propulsion engine could provide constant and efficient thrust, essential for covering the immense distances between stars. Another even more advanced and theoretical concept is warp drive propulsion, often discussed in science fiction. Based on current theoretical concepts, like those proposed in Einstein's field equations of general relativity, this form of propulsion would involve the ability to warp spacetime around a ship, allowing it to travel at effective speeds faster than light, without violating the laws of physics. However, the practical realization of a warp drive would require extraordinary advancements in physics and a deeper understanding of the fabric of spacetime. For missions lasting years or even decades, life support systems must be exceptionally advanced and fully autonomous. This includes closed-loop systems for water and air regeneration, food production, and waste management. The technology should ensure not only survival, but also the physical and psychological well-being of astronauts over long periods. Interstellar missions will require efficient systems for resource and energy management. This could include the use of mini-nuclear reactors for energy, advanced systems for collecting and utilizing solar energy, and perhaps forms of energy harvesting yet to be discovered or invented. Another crucial aspect is the development of technologies for interstellar communication. With immense distances, communication between the spacecraft and Earth might require new methods, such as the use of quantum communication networks or space relays. The 23rd century and beyond represent an extraordinary phase in the history of space exploration, where humanity extends its reach to distant star systems. The key to reaching other star systems lies in the ability to travel at speeds vastly superior to current capabilities. This could be made possible through technologies such as nuclear fusion propulsion, photonic propulsion engines, or even warp drive. These methods could drastically reduce travel times, making interstellar journeys feasible within a human lifetime. Progress in this field also requires a deeper understanding of fundamental physical principles. This might include new theories and discoveries in quantum physics, relativity, and perhaps even concepts not yet imagined, which could unlock new possibilities in propulsion and spacetime manipulation. To survive and function in interstellar space, advanced materials capable of withstanding extreme conditions, such as intense cosmic radiation, high-speed space debris, and extreme temperatures, are needed. These materials could be based on nanotechnology, metamaterials, or advanced composites, offering strength, lightness, and self-repair capabilities. Missions at this level are not limited to mere exploration. They also involve finding and potentially colonizing new habitable worlds. This will require a tremendous amount of research and development in fields like space ecology, bioengineering, and terraforming to create sustainable environments for human life far from Earth. From the 23rd century onwards, humanity would begin to push beyond the limits of our solar system, exploring and even inhabiting worlds that we can now only imagine. This era of interstellar exploration represents not just a technological leap, but also a fundamental shift in how we view ourselves in the universe, no longer as inhabitants of a single planet, but as citizens of a much vaster galaxy. This timeline, designed by NASA scholars, represents more than mere exploration. It's a journey of survival and discovery. Every step, every leap, brings us closer to answering the fundamental question: are we alone in the universe? And on this journey, we may discover that our greatest challenge was not reaching the stars, but surpassing ourselves, our great filter, and ensuring that our cradle, Earth, never becomes the end of our story. Imagine a future where stars are not just points of light in the night sky, but destinations, new homes, new hopes. Every new world we touch becomes a canvas for our dreams and aspirations, a new chapter in the story of humanity. This space expansion is not just an escape from threats, but an embrace of our cosmic destiny. It's a reminder that, despite our fragilities and challenges, we have the capacity to overcome our limits, to be more than inhabitants of a single planet, but true citizens of the universe. Space expansion represents our commitment to pursue the future, to challenge the unknown, and to ensure that the light of humanity continues to shine, not just on Earth, but throughout the cosmos that awaits us. It is an anthem to our intelligence and indomitable spirit. NASA's model envisions a humanity capable of colonizing space and conquering new worlds, and today we can witness the beginning and success of this marvelous adventure. Let us know in the comments what you think, and if you haven't already, subscribe and stay tuned for new videos to support the channel. Until our next journey.